So we had done a lot of physics with the hydrogen atom, the lightest, the simplest, just one proton and one electron, but it can teach us such a rich physics, and especially the quantum physics that I could do with this hydrogen atom. We talked about wave particle duality of light as well as of electron, the energy and momentum of a photon, how are they related with wavelength and frequency of the corresponding wave. So the light has both the aspects. If you talk of intensity of light, it is a number of photons striking a small area per unit time and so on. So how many photons are reaching there, and this number is or this intensity is also given by that amplitude square of the electric field in that wave. So the wave is determining the probability of finding the photon there, or how many photons are reaching there. In a similar spirit, we talk for electrons also. There also you have wave particle duality. Electrons have energy, electrons have momentum, you can count electrons, they are particles, but then there are waves, they are diffracted, you have all those electron microscope, everything, and the wave aspect of electron can be dealt with this wave function. So this wave function decides the probability of finding the electron at a particular place, and to get that wave function for a fixed energy state, we have that Schrdinger equation, which has some boundary conditions and other things. Those things we talked, and a formulation of this mechanism, which is not based on Newton's law, but based on this Schrödinger's equation, that we could tell with hydrogen. Now we have these quantum ideas, and these quantum ideas we will be using later, and this is the time when I really move one step ahead and talk of atom with more than one electrons, a multi-electron atoms. How do electrons behave in an atom if there are several electrons in that atom? So that quantum mechanics we will be discussing in today's lecture. So if you have an atom with Z protons and few neutrons naturally in the nucleus, and then there are Z electrons, and you pick up one electron and ask what is the energy of this electron in the field of that rest of the atom, and what are the wave functions. So the Schrödinger equation would be something like this. If that electron that you have picked, you label it as ith electron. Now this is another important idea, that can you distinguish between different electrons in an atom? They are distinguishable or they are indistinguishable. So that's a very interesting separate story, but let us say that I am looking for that ith electron, and there are total Z electrons. For this electron, what will be the Schrödinger equation? It will be minus h cross square over 2m del square, but this time this del square means del 2 del xi square, del 2 del yi square, that I will be there. It is the ith electron. Its coordinate is described as xi comma yi comma zi. These differentiations are to be done with respect to those coordinates. If I am talking of some other electron, jth electron, that position vector will be described by some xj comma yj comma zj. So for that, if I am writing the equation, this del square will mean del 2 del xj square and so on. So this is it, and then psi, this psi will be a function of this coordinate of ith electron, plus what will be the potential energy function. the potential energy function will be minus ZE square over 4 pi epsilon naught Ri and plus summation over E square by 4 pi epsilon naught and then this mod Ri minus Rj, summation is over j not equal to I. This is the potential energy function. What is this? The first term here is the potential energy because of this ith electron and the nucleus. So you have this nucleus has plus Ze charge, and then you have certain electrons, and let's say this is that ith electron, then this distance Ri. So there is a potential energy of this electron with this nucleus here, and that will be minus E here and plus Ze here, and therefore this term. You also have potential energy of this ith electron with this electron, with this electron, with this electron, and so on. So if you pick up some jth electron, okay, you pick up some, suppose this is that jth electron, then this vector is Rj and this vector is Ri, and therefore the distance here is this mod of Ri minus Rj. And this is minus E charge here. This is minus E charge here. So the potential energy will be Q1, Q2 minus E into minus E. That will be this E square divided by 4 pi epsilon naught, distance between the ith electron and jth electron. So this will be UR, and then you will have that wave function here and E psi here. A very complicated equation in the sense that all these other electrons are not stationary, not at their own place. So per instant, every instant they are also changing their probability distribution, and therefore this writing this potential energy function, solving, it's a difficult story. But then a much easier model can be worked out, very close to reality, and that is this whole thing, this whole potential is equivalent to some kind of an average potential seen by this electron because of all the other electrons and the nucleus, and all they are changing their probability distribution, everything, but still all this can be approximated by a particular simple function which is a function of this R only. So if I am looking at one electron, the entire rest of the atom is providing some kind of a potential here, potential energy function here, which depends only on R, not on theta phi, not on directions and all that. It's not that Coulomb 1 by R type, but some central potential can be worked out. Okay, so this is some central potential. What do we mean by central potential? This depends only on the distance R. Okay, depends only on R, not on angles. That is known as central potential. So the solution of Schrdinger equation with this kind of a central potential, if it is known, is much easier than dealing with this one. And the essential features that we discussed with Coulomb force or Coulomb potential energy, many of them are applicable for this kind of central potential also. Coulomb potential is also central potential, right, minus E square by 4 pi epsilon naught r, only distance. So all those things are valid, and I can still say that the wave function is characterized by 3 parameters, n, l and ml. Okay. And the same things, n can go from 1 to 3 like that, positive integers, l goes from 0, 1 up to n minus 1, all those things will be there. ml will go from minus l to plus l in steps of 1, all those things are still valid. And of course the spin is there, so ms is always there, and that has nothing to do with this potential and all that ms can be plus minus half, and accordingly you can have this chi ms at the spin part of the state. So these things are still valid. The difference, one difference is that energy corresponding to these quantum states, they now depend on n and l. For Coulomb potential, it only depends on n. If your potential is 1 by r type, then it depends only on n, not on l, not on ml. But if it is central but not of Coulomb type, then energy depends on n and l. So we don't write En, we write Enl. Okay. So that means suppose n is equal to 2, and then you have L which can be 0, which can be 1, that means you can have 2s, you can have 2p. Now 2s will have one energy and 2p will have a different energy. It depends on n and l. It still does not depend on ml and not on ms. So your energies are now labeled as energy of 1s, energy of 2s, energy of 2p and so on. And the number of quantum states are still again given by the same thing which we had done just now. That means all S states, right, all S labels, all S groups will have 2 quantum states. 2s will have 2 quantum states, 1s will have 2 quantum states, 3s will have 2 quantum states. All p groups will have 6 quantum states, including the spin plus half and minus half. So 2p, 3p, 4p, they will all have, each of them will have 6 quantum states. So that counting will still remain like this. So what we get from these solutions is a number of energy states, and each energy state will have some quantum states there, and then the electrons, for each electron these are available. So let me draw a line diagram for that. So let me draw the energy levels. The lowest will be 1s, n is equal to 1, l is equal to 0. Then the next one will be 2s, then you will have 2p, then you will have 3s, 3p, then you have 3d and 4s, and there generally 4s is slightly lower than 3d, but this can also get swapped, depends on which atom you are talking, but most of our discussions will be up to here 3p. This order is for all atoms which we will be concerned with. This order is okay. You have 1s energy level lowest, then you have 2s, 2p, 3s, 3p, and then others. Don't look at the relative magnitudes. It is only giving the order, which one is lower, which one is higher. So it's not to the scale for any atom. So this is the kind of energy level diagram you still have. And this is energy for each of these z electrons. Okay. So in the atom you have z protons plus neutrons, and Z electrons. All these Z electrons are treated at equivalent ground. So each of these Z electrons will have these energy levels, and anyone can go anywhere. Now if you want the lowest energy of the atom, then the best way is to put all these Z electrons here. Put all these Z electrons here and the energy will be lowest. But we cannot do that. And we cannot do that because of another wonderful quantum mechanical principle, and that is, for any spin half particle, a quantum state cannot have more than one particle in it, identical particles. So if you have electron, which is a spin half particle, so you have several electrons and you have a quantum state here, you can at most put one electron in this quantum state. In this quantum or any quantum state, you cannot put more than one electron. Either the quantum state will be unoccupied or it will be occupied by one electron. That is it. This is known as Pauli exclusion principle. Pauli exclusion principle, it tells that in one quantum state you cannot put two electrons simultaneously, and this is true for all spin half particles. For protons also, if you have in a nucleus, if you write those energy levels and quantum states, then you cannot put two protons in one quantum state or two neutrons in one quantum state and so on. So here in this 1s you have two quantum states, right? All s energy levels, they have two quantum states. All p energy levels, they have 6 quantum states. So at best you can put 2 electrons here, 2 quantum states, 2 electrons. Then if you have more electrons, 2 electrons means helium. If you have helium atom, Z is equal to 2, so that is helium atom. So for helium atom in ground state, both the electrons can be put here. If you go higher, suppose you have Z is equal to 3, lithium, you have 3 electrons, 2 electrons for lowest energy state, 2 electrons will go here and the third one must go here, 2, and then for lithium that next electron should go here. If it is beryllium, Z is equal to 4, beryllium, then the fourth electron again goes here and it becomes 2 electrons here. So this is how it is filled from below. For ground state of the atom, you have to put all those Z electrons in these levels, but then take care that in one quantum state you put only one electron. Suppose you have sodium, Z is equal to 11, you have sodium, so 11, so 2 you can put here, 2 you can put here, 4, 6 you can put here, 10, and the one left you can put there. So for lowest energy state, lowest energy of this sodium atom, the electrons will occupy in this fashion. Remember, all electrons are identical. All electrons are identical. Which electron is where, that is not important. The only important thing is 2 are here, 2 are here, 6 are here, 1 is here, and these are all energy levels. So in an atom, if you want to picturize, you can say that you have this proton here, Ze, this plus Ze charge here, and then you have Z electrons which are in some states. You can picturize, we did that based on the probability distribution and all that, but just to have a very rough idea, you can say that okay, this is 1s, and then you have let's say 2s, and then you have some 2p, you have some 3s, and so on. So you have 2 electrons here, then in 1s you have 2 electrons, then in this 2p you have 6 electrons, somewhere in this 2p you have, and then in 3s you have 1 electron, and so on. So this is how you can picturize. Now suppose you have sodium vapor. Vapor means you have a collection of atoms, you have large number of atoms, but it's vapor. That means the average separation between the two particles is quite large, reasonably large. Large with respect to what? Large with respect to whatever parameter you take, radius of this atom. The radius means where up to where your electron wave functions are significant, or in many ways you can put a scale. So suppose now you have sodium vapor, what happens? So let me remove this. So suppose you have sodium vapor. And suppose you have n atoms, capital M atoms in wherever you put this vapor. So there are n atoms. Now since it is a vapor, the average separation is large. One sodium atom is somewhere here, another is quite far away. So you have 11 electrons here and also 11 electrons here. With each atom you have 11 electrons. And pick up any electron from any atom. What kind of potential it is seeing? Suppose you pick any electron, what kind of potential energy function it experiences? It is the same nucleus and this electron, that interaction, then its interaction with rest 10 electrons. So that is the potential energy function. And you come to this atom, same potential distribution, same potential energy function. If you pick an electron from here and ask what is the kind of potential energy function it is, once again you have a same nucleus, 11 protons. So you have that Coulomb potential with nucleus. Then there are 10 more electrons here. So same kind of potential here. For any atom you pick, the potential energy function is the same. And if potential energy function is the same, then the solution of Schrdinger equation is also same, because Schrdinger equation is only that potential energy which can change, otherwise everything is same. Electron is there, so mass of electron will be there, and then the remaining equation is all the same for each of these electrons. So that means for each atom you have 1s. This can be for lowest energy state, 2 of the electrons should be in 1s. 2 of these electrons should also be in 1s at the same energy, because it's the solution of same Schrdinger equation. So n equal to 1, L equal to 0, that energy level, it's same for this one, this one, this one. So at this energy itself, 2n electrons should come here, assuming that each of these atoms is in its ground state to have the lowest energy. So 2 of 11 must be here, and there are capital N atoms. So these many electrons are at this energy, and these many quantum states are there. For one atom you have 2 quantum states, and for n atoms you have 2 times n quantum states. This is the number of quantum states. All this is at the same energy, that lowest energy, ground state energy of one atom. So if it is one atom, you have two quantum states. If it is n atoms, you have two n quantum states, and each quantum state is occupied by one electron, and therefore 2n electrons are here. Similarly, here also you have 2n quantum states and 2n electrons are here. Here you have 6n quantum states and you have 6n electrons. Remember, Z is 11. So for each atom you have 11 electrons. 2 go here, 2 go here, 6 go here, and therefore 6n electrons, 6n quantum states, they are filling from below in energy, and now you are left with n electrons. So n electrons will come here and 2n quantum states are here. So this side I am telling number of electrons, this side, this one, this one, this one, this one, and this side I am telling number of quantum states at that energy. So this one, these are number of quantum states. So what do you find? At this energy, all quantum states are full. At this energy, all quantum states are full. Similar case here. But at this energy, half the quantum states are full and half the quantum states are empty. Quantum state is there, but no electrons to occupy that. So this is the structure if you have sodium vapor. But we are interested in solids, not in vapors. So what happens to this energy level diagram? If you bring the atoms closer and finally make a sodium crystal. Sodium has its own crystal structure. So a solid sodium will be like that. You will have all those ions at place, at proper place, electrons and all that. So that crystal type structure. So what happens to this energy level diagram if you reduce the separation gradually and finally make it a solid? So that will be our next topic.